Hello, Mr. Teo. Today I'm with my group mates.
My name is Gan Xue En and I am from DMTE.
My name is Jaryl from DMTE.
My name is Wong Qi Hang. I'm from DEE. Today we will be presenting the applications of differentiation in analyzing the rate of change of voltage in solar photovoltaic systems. This is a brief presentation outline. So, solar photovoltaic systems are an important source of renewable energy and are increasingly used as an alternative to traditional energy sources. However, their performance is not always stable as it can be affected by environmental factors such as temperature changes as well as structural issues like mechanical stress or microcracks. These factors can cause fluctuations in the voltage output, which reduces efficiency, may also indicate underlying damage in the system. If these changes are not detected early, they can lead to more serious performance issues over time. So to better understand these fluctuations, we use differentiation, which allows us to measure the instantaneous rate of change of voltage. In other words, instead of just looking at average values, we can analyze how quickly the voltage is changing at any given time. Next. Moving on to the main problem of this study is that voltage output in solar PV systems are constantly changing due to external and internal factors. However, traditional monitoring methods often focus on average values, which means sudden changes or rapid drops may not be detected immediately. This can be a limitation because early signs of faults or damage might be missed if we rely on average measurements. So to address these problems, we have set two objectives. First, to apply differentiation to analyze the instantaneous rate of change of voltage. Second is to investigate how structural dynamics such as temperature and mechanical stress affect the voltage output of PV systems. I'll be passing it on to Jaryl.
Next is a methodology part of the presentation. This is the first slide. As you can see, our solar panels lose power when they experience heat or physical stress. To show this mathematically, we use exponential relaxation model, which is this one. We set three main parameters based on past research: an initial voltage of 20, the final setting voltage of 10, and a time constant which is 5 seconds. We put these three numbers into the general formula, which is this. To find out exactly how fast the voltage drops, we need to find its derivative. To do this, we use the three basic calculus rules that you can see at the bottom: the constant rule, the multiple constant rule, and the exponential chain rule. Now let's look at the actual math. Here is a step-by-step derivation of our rate of change, which is dV over dt. The first step, we start with voltage, the voltage function, which is Vt equals 10 plus 10 times e to the power of negative 0.2t. In step 2, we apply the constant rule to the first number, 10. The derivative of a constant is always 0, so this part disappears. It becomes d over dt, 10 equals to 0. In step 3, we use the constant multiple and chain rules on the second part. We take the derivative of the exponent, which gives us negative 0.2. When we multiply that by 10 in front, it becomes d over dt, 10 times e to the power of negative 0.2t equals 10 times negative 0.2 times e to the power of negative 0.2t. That brings us to step 4, the final answer, which is dV over dt equals negative 2 times e to the power of negative 0.2t. This equation is very important as it lets us calculate the rate of voltage change at any given second. This helps us engineers find the sudden system fault instantly, rather than waiting to look at average numbers.
So this is the numerical result that we use in our report. So as just now Jaryl said, we can use these two VT and also dVdt equation to calculate the voltage and also the rate of change. So when we need to sub different value of t, because we can, by calculating the value at different time point, we can show that how the system gradually move from the initial to steady state, and also we will not miss the what happened in between. So it is a simple equation, so we can just sub the t. If our t is equal to 0, we can just sub the 0 inside the vt and also the dVdt equation. So we can get, when the t is equal to 0, the voltage is steady, and when the t is 0, our rate of change is -2. So use the same way to calculate t equal to 2, t equal to 5, and t equal to 10. So this is the result table for and then this is the graphical analysis for this graph. It shows the transition behavior of voltage. So when the t is equal to 0, the voltage is equal to 20 volt. So at the end, when the t is equal to 10, the voltage decrease become 11.35. So, and the other graph is show the rate of change over time. So initially the rate of change is -2. So means that the voltage is decreasing. And the last graph is a combined graph with these two graphs. The blue color line is represent the voltage, and the red dashed line is represent the rate of change over time. So this slide summarize the key observation and interpretation from the graphical analysis. The first one is exponential decay behavior and rapid initial response. The next one is system stabilization, and the last is advantage over average monitoring.
Next is the conclusion and limitations. Our main conclusion is here on the left, is that calculus works well for this problem. Using differentiation helps us track the rapid voltage drops right as they happen. This is a big improvement over the old methods, which only measure the average voltage over time. Next is the limitations and recommendations. However, this study has few limits. This model assumes the weather, temperature never changes, and we use simulated computer data instead of real-life testing. To fix this, in the future we recommend testing this math with real sensor data from actual solar farms. We also suggest using second-order derivatives and machine learning to make the fault detection completely automatic. Next. These are all the references used in our study. That is all. Thank you.